Hi everyone, my name is Alex Kingsbury. I'm from NLife and I'm really pleased today to introduce our first talk for Wednesday. We're going to be listening to Alex Richard, who is the GM for Additive Solutions at DMG MORI. And we're going to be listening to Dr. Martin McMahon, who is an industry consultant for MAM Solutions and also a technical advisor for Metal Additive Manufacturing magazine. We recently had a really great article in Metal Additive Manufacturing magazine that Martin did a lot of technical advisory for us on, and included in that article was a lot of really good information from DMG MORI and how they've been able to reduce dollars per kilogram for additive manufacturing using beam shaping. Today we're going to hear about a case study in stainless steel. This is a real case study. It's a real application. And it's an example where we've been able to take something from traditional manufacturing, metal injection molding, over to additive manufacturing and do it economically. There's a business case behind it that supports it. This is about beam shaping, making business cases work. Thank you.
Thank you, Alex. Welcome everybody. This is really an interesting case study actually, because as Alex has already mentioned, it's taking something from what is almost a conventional production method. I wouldn't quite say MIM is fully conventional today, and it's not necessarily one that you would immediately consider a candidate that you would switch over from conventional to additive manufacturing. So that makes that quite interesting. So perhaps, Alex, you could start by just introducing what it is that this case study is actually about.
Absolutely. Hopefully the volume's good there. So this is the part that we're talking about today. So this is a housing for a digital indicator made by a sister company of ours called Magnescale. So they make a lot of high precision components, linear and different types of encoders, laser encoders, magnet encoders, as well as these different types of measuring devices. And so this is a situation where they came to us and said, hey, we're developing this new product. We're looking for alternative ways to manufacture this product that has improved cost, has improved flexibility in the manufacturing process and getting ramped up compared to what they'd have to do for something like MIM, which would be the traditional way of making these parts for them.
So this being effectively an internal project, the sister company, I imagine that also it's not exactly a high volume part this to manufacture. So they've got MIM in mind already to manufacture. Was the cost constraints a consideration for when you made the decision to switch over to laser powder bed for this application?
Yeah, definitely. So cost constraints were arguably the main factor. We have a general push at DMG MORI to do more additive manufacturing for ourselves. So we make all different kinds of machine tools. We make automation products. We make obviously additive machines, but we also have sister companies like Magnescale who are producing various components. And so we have a desire to do more additive manufacturing, to get, understand how to do it ourselves, but also look for ways to improve our processes, improve our products, bring the cost of our products down through additive manufacturing. So that was really one of the drivers here, was just finding ways to reduce costs from a traditional, in this case, quote unquote, traditional approach to manufacturing these types of parts.
Right, and I understand that this solution is actually a solution that's actually also been fully developed in the US. So DMG MORI, they obviously acquired a technology in 2017. It's been developed and continued to be developed in Germany, but this is a project which is solely based in the US, I understand.
Yeah, and actually, let me, quick overview here. So for those that don't know DMG MORI, we do a lot of stuff, right? So our traditional technologies are milling and turning, but over the last 15 or so years, we've started to get more into additive manufacturing. So it started with DED hybrid machines, so implementing DED processes into our existing milling and turning platforms. That, as you said, in 2017, we purchased a company called Realizer. It was one of the early pioneers in developing the laser powder bed fusion technology in Germany, brought them into the DMG MORI fold, and then started to develop new products based on those platforms over the last number of years. So up until recently, that's primarily taken place in Germany, in our factory in Bielefeld. However, starting this year, going into next year, we're producing a new platform in the US in our Davis, California factory. And that's what we're focusing on for this product here.
And that laser SLM solution, not SLM solution, sorry, excuse my slip there.
No, so actually, no, so it's kind of a good point because we get this question a lot. So we use the term SLM also. So the reason for that is because the founder of Realizer, founder of SLM Solutions, were in the same research group in Germany back in the day, and both have their names on the patents for SLM.
Okay, that's interesting.
And so that's where that origin comes from. So it's basically tied to both companies for that reason.
So the third generation machine's actually still being made in Germany, but this is a special project that's actually coming out of the Davis facility.
Correct, Davis, California. Yeah. So. So if you go into our booth over there, you can see the third gen machine that's coming here out of Bielefeld. Starting next year, we'll be also shipping the machines out of Davis, California. So traditionally, that's a factory where we're making horizontal milling machines. Other things over there over the years, 5-axis milling machines, lathes as well. But primarily, it's a horizontal milling machine factory. But due to a number of different market forces, we realized that producing additive manufacturing machines in the U.S. has a lot of advantages. And so that's one of the new projects we're ramping up in that factory is to produce this new SLM platform in Davis, California.
And is it the both platforms, the third gen and the US version, incorporating the AFX laser, or is it just
so for now, we're starting with the US machine. Okay. In the future, there will likely be more options on the third gen machine as well. I can say that.
Okay. So, and what particular aspects then of the beam shaping technology made that more suitable for this particular case study?
Yeah. And so I guess maybe kind of taking a half a step back there. So the general idea behind this US machine is, one, to have a machine that's made in the US that helps appeal to a lot of different customers who that's important for. But also we're looking into this machine to basically lower the barrier entry for people who want to get into additive manufacturing. So traditionally, this is a space, obviously, as we all know, that relatively expensive, relatively high investment to purchase equipment, to ramp up production, all the peripheral equipment that's involved. So our goal here is to really bring the complexity and the cost of the machine down to a point where new users who might be our existing traditional manufacturing base that DMG MORI has, who are not doing additive, are now able to find opportunities and business cases that allow them to enter the additive space and be productive and make money in the additive space with this machine. So the reason that we like the N-Light lasers for that purpose is that it allows us to, with a single laser system, get productivity of a multi-laser system while still keeping the cost down because we only have one laser in the machine.
I see. So you've mentioned it's a single laser system, but the third gen system can have 1, 2, and maybe 4 lasers.
Our third gen system is anywhere from one to 4 lasers. In the US machine, starting now is a single laser system. There will likely be opportunities to expand that in the future as well on that platform. But we're, the first machines coming to the market will be single laser systems.
But you developed other technology in that third gen machine. Is that carried across into this system, even though it's a smaller, more compact and more economic system?
Yes and no. There's certain aspects that transfer over, and some that have been inherited from the German platforms. But there's a lot of really new stuff in the US machine that's unique to that machine as well. So I mentioned before, it's a little bit simpler, if you will. So one really cool aspect of our German machines is that we have a closed loop powder system to help maintain the quality of the powder and minimize contact with the powder to the user. We have other options there to have different types of powder handling systems as well. US machine is simpler. We just have simple upper hopper, lower hopper. We do all our sieving offline. We don't have that closed loop system. So it helps keep the complexity down, the cost down a little bit. But we also have an interesting new recoder we've developed specifically for this platform. So it's an electrostatic non-contact recoder. Okay. So what it does is it brings the recoder across the powder bed. It uses electrostatic to kind of resettle the powder bed as it goes. So without contacting the powder bed, we're able to get a nice, clean, consistent powder layout. And it's a really interesting new technology that we do have on that US machine that has not yet come to the German machine.
So in terms of the beam shape technology, this is obviously quite a small component. We've seen the images there. We've got samples on the desk here. You can see quite a lot of detail in that. Are you using any particular aspects of the different beam modes?
I'll go back up to the picture, hopefully, if I can get the flicker to work so you can see the pictures up in big. But There we
So
go.
obviously one of the advantages of doing MIM is that you can actually achieve quite high detail directly in the MIM process.
Correct.
How
Yeah.
are you achieving that with a laser powder bed?
Yep. So in this case, this part actually has some very tight tolerances on it. So it's housing. It's not critical from a functionality perspective, but it is critical from just having it fit together properly, and the visual aspect of it is important to make sure it all fits together and seats together nicely. So regardless if it's MIM or regardless if it's powder bed, there's still a lot of machining that has to go into it after the fact. Right. So that's a variable that we haven't been able to remove specifically by printing it as opposed to MIM.
Okay, but with the switch from MIM to laser powder bed, that you're obviously not having to do tooling anymore or anything, so there must be a cost benefit in it.
Correct. Yes, 100%. So there's the machining and tooling and the fixturing for that, but as far as the develop of the tooling of the molds for the MIM process, that whole cost is out the window now, so we don't have to worry about that cost. And that was a big driver for Magnescale wanting to look at this process, because they didn't want to have to do that investment in the tooling up front for the MIM process. They didn't want to be locked into, once they've done that tooling, not be able to change designs. Like I said, it's a new product, so there may be some adjustments they're still making to how they want to bring this to market. So they wanted to look at ways that it could be flexible as they're going through this process and have quicker response times to developing new products and developing new manufacturing processes. So additive is much more conducive to that approach than having to invest in that upfront tooling from it.
And do you get an advantage because you're using a laser to fully melt the powder now, that you're not having to do a heat treatment afterwards? Because obviously with MIM you have that step where you have to do a sintering and maybe other subsequent heat treatments. Do you get that now just in one single hit by just doing the melting and nothing else?
Yeah, 100%. So I think ultimately it comes down to lead times and costs is where the advantage of having the simpler processes. You don't have to go through the multiple steps in the sintering process that MIM has. Like I said, it's a housing, so there's not critical mechanical properties we're trying to achieve necessarily that we get advantage of from the laser powder bed fusion process. But yeah, I think just the overall simplicity of the manufacturing process is preferred here.
And is it the same material that you've switched from MIM to the additive, or?
On the MIM side, there's a low carbon steel.
Okay.
So we've switched over to 17.4 for this. Just because that was
carbon steel, not exactly suited for additive.
Not suited for additive, so we just switched over to an existing material that's already suited for additive, that's already proven out. Again, the main critical thing here was just making sure we were similar in the thermal expansion coefficient, making sure we're not having wildly different performances in different environments for the part. But again, mechanical properties, we just needed something similar. Yeah.
Right. Okay. So you're not actually then doing that hardening treatment of the 17.4. It's just because it's a convenient powder, I guess.
Correct. Exactly. So it's I think we're as printed in this one. We're in the low 30s HRC, which is fine for this application, but there wasn't a critical requirement there for that. So
okay. So and MIM traditionally is used for quite high volume manufacture as well, and this is quite a reasonable size machine. I'd class it as a medium sized machine, single laser still, but 300 millimeter square bed.
Yep.
Looking at the size of the parts, you can probably get quite a few of those in a build, and there's two parts. Are you building them together as a kit so that they're assembled, or do you split it up in some different way?
Yeah, no. So we're building them. We basically break them up into different builds for the main body of the case and the covers. So we're getting about, for these main bodies, 40 on the plate right now. That fits well into our entire process chain, because we also have a tombstone that we then take the 40 parts off the build plate, put them into the tombstone in the milling machine for post-processing, for finishing. And so we can take the entire build, put it into the machine, and have that seamless process and machine all the parts in one go.
So you've got the advantage really, because obviously DMG's got that legacy or that history of machine tool, and you've got the whole process chain under your control.
Absolutely. Yeah. So and that's one advantage I think that we can bring to a sister company like Magnescale, but also other companies, is that we have experience with the printing side, we have experience with the machining side, we have experience with the automation tools to help ease that process and improve that process as well. So for example, that we're machining these on a NHX 4000 machine. So
okay.
It's a horizontal milling machine, 30,000 RPM spindle. So very high speed spindle, which is helping for machining some of these small features in the part.
And that's the same machine coming out of the Davis facility?
We're also making that machine at the Davis facility as well. Yep.
Okay, that's interesting.
Yep. And so that machine has options to have built-in pallet systems, which are really interesting for being able to take a build plate, for example, off the machine, put it directly into the pallet system, and then have that machined immediately, and then also have that go into an automated system that can swap out jobs. So you can be machining one build job, pull another, one off a different machine, put it in the pallet system. As soon as that's done, you can start automating that process to go in and do post processing.
Is that the same with the covers though? Because obviously the covers are a lot smaller. You can get a lot more of them in a build.
Yeah, honestly, I don't remember how many covers we put on the build plate. It was more. So the covers have same concept, but different fixture setup process and different build preparation process. Right. But yeah,
and I see it's quite popular these days that people are trying to stack and fill that build volume. You've got a quite high build volume as well, but I understand you're just doing one layer at a time.
One layer at a time for now, just because the quantities of parts we need to produce per month don't require us to stack them.
Thousands.
Yeah, okay. We're looking at about 500 a month right now is the ramp up for this. So
that's still reasonable production numbers though for additive. I mean,
yeah, exactly.
Still struggle to understand additive as a potential for production, and hundreds are certainly nice numbers to hear about.
Yeah.
What about the actual finishing though? I mean, obviously as an additive part, there are things like support structures that need to be taken into consideration, which you wouldn't normally have in MIM. Does that add extra complexity in the post-processing?
There's a little bit of additional machining that has to happen for this, because we do have those support structures, and we're also building in some additional structures to hold the part, to probe the part once it's in the machine, to make sure we can locate it properly. So some of those things we don't have to put into the MIM process. So there's a little bit, I think it's about 25% more machining that goes into this, but we're seeing an overall reduction in the cost per part of about 38%, because the entire process is more efficient, and the cost of producing the near net shape that we're starting with through the additive process versus the MIM process is significantly less, I think about 58% less.
And the final step's the same regardless. So I understand they're all electroplated anyway.
Correct, exactly. So the general process, is you create that near net shape either from MIM or from additive, and then we're machining it, again, slightly different machining process, but comparable. And then afterwards they get out and get electroplated for final finishing process. So that doesn't change at all. So it's the same regardless. Yeah.
Okay, interesting. So in terms of just coming back to the machine itself, it's got one laser currently. Does it have that ability to expand? Would you consider putting in more lasers in the future if the demand came?
Yeah, there's plans to have more lasers in that platform in the future. There's plans to have higher laser power in the future as well. So there will be more updates coming to the platform.
Right, and then this is obviously just your first case study, which happened to be for a sister company, made it quite easy. But are you also working with other external partners that are looking for that bigger opportunity to really show what the capabilities of beam shaping are? Because
absolutely,
I imagine you're only using maybe one or two modes at most at the moment in this application. But
yeah, this is primarily mode 0 for contours, mode 6 for hatch. So nothing too crazy, nothing too fancy on there, but again, very effective, which I think is good, right? Not every part has to be a most complex part, right? We want to show that we have good business cases, we have interesting opportunities to do quote unquote simple things with additive. I think that's a big part of expanding the additives market a little bit.
And do you see this possibility going into the other third gen machine as well with this technology? Some of us have been kind of waiting for beam shaped technology for a number of years. It's really quite an exciting development. Personally, I find it's one of those things that could open up quite a lot of applications. Mm-hmm. So do you think there are other applications which DMG have already got their eye on that they'd like to try and explore more with this beam shaping?
Yeah, definitely. I mean, there's other, I can't speak to some of the details, some proprietary things, but for example, we've had parts that have won races that were made with the beam shaping technology that have gone into race cars already this year. We have parts that are being delivered and in use that have been done with beam shaping already, but there's a lot more on the horizon, and that third gen platform is designed to be upgradable, let's say.
Okay. And one of the problems we see in additive quite often is when things change, it's already a new and disruptive technology. You bring in a new technology or a new ingredient to the technology. In this case, it's a new laser beam. Are you having to requalify all the materials again because you're putting that into a new platform as well?
I mean, there's obviously verification. We found that the parameters that have been developed already for our Gaussian beams translate pretty well to mode 0. Some minor adjustments. However, getting into mode 6, there's more parameter development that goes into mode 6 and the other modes as well. So there is some additional work to do there.
Yeah, and quite a lot of material science, I'd imagine, because one of the benefits of this, especially the ring beam configurations, that you can maybe control microstructure a little bit more and then tailor your mechanical properties. So there'll be quite a lot of development.
Absolutely, I'm excited to see what work goes into figuring out exactly what we can do with this technology. I think really we've just scratched the surface so far of what we can really do.
Right, and the system you're building, like I said, it's coming out of California, but it's intended to be shippable for the rest of the world through the standard DMG
correct exactly yep.
distribution network.
Yep, starting next year will be available anywhere through our normal channels. Yep.
Right. Okay. And what about the control then and stuff? Because it's a different way of controlling the beam. You've got different strategies, different scan possibilities. Do you have different software capabilities and different?
So we have our control software is called Celos. It's our own proprietary control software, and within Celos we've developed a very easy, simple interface for programming which mode you're using at which point in the process, and it's all done through our software. Very easy, very seamless. We call it adaptive beam control, kind of as our own kind of proprietary take on it, but it also gives us a lot of opportunity to really customize that user experience. So
right, okay, well, I'm done the questions I've got. I don't know if we want to open up to any questions in the audience. So thanks for listening so far. But if there's anybody who wants to ask any questions of DMG, then now's your opportunity.
Okay, Alex, I've got one.
Yes.
So I'm really curious about there was a great example of how you got to 38% lower cost. Might be getting a little feedback from being in front of that. Yeah. Tell me, if you used a standard single mode laser based machine, powder bed fusion machine, do you get to a cost structure that's lower than the MIM?
No.
Okay.
No.
So that's the key point.
Correct. Okay, yeah. So I mean, I don't have those numbers off the top of my head for what the single laser would be because we didn't do it. I don't have it here. But typically we're seeing in most of our feasibility studies, most of our test cuts, most of our work we're doing, that what we get, the productivity we get with the beam shaping laser is very comparable to our dual Gaussian laser systems. So that's our general rule of thumb that we see consistently.
Yeah. That's actually quite remarkable when you think about it, though, because effectively said that they're only using 2 of the beam modes that are available, and most of that work is actually in the contour, which is the zero mode itself. So it's very similar to a Gaussian beam. So to be able to get that kind of level of cost reduction.
That's one thing I think is interesting, though, because my thought when I started understanding and learning about beam shaping and learning about the different modes is, okay, well, a part like this, you wouldn't really use mode 6 at all. You wouldn't use the other modes. It's mostly small features, right?
Yeah.
But a relatively small feature when you're looking at it is actually a pretty big feature when it comes down to the spot size of mode 6. So you can actually use mode 6 a lot more than you realize on these parts that so it's not a lot of infill. It's not a big chunk of material. It doesn't matter. Mode 6 this will be really productive in those situations.
And what actually is the nominal spot size then?
About 240 microns.
Okay. In spot 6, in the mode 6.
In the mode 6, yep.
Okay.
Yeah, we range from about 80 in mode 0 to about 240 in mode 6.
Interesting. In fact, a question for you guys, I suppose, really is you just announced the 2000 watt version of this laser. In my mind, that means that you can also go to much bigger spot sizes. Is that something which is more dictated by these guys with the optics that they apply, or is that something that you've got more control of?
Yeah, good. The 2000 watt laser will have a larger spot size in mode 6 by just about 10%.
Yeah.
Not dramatic, but the 2 kilowatts of power will allow for like putting zoom optics in front of that to then get that 240 micron spot size to something considerably larger for the same intensity, right? So therefore, we expect a similar amount of spatter and evaporated condensate for the process with a much faster process.
Yep. Be able to push the envelope as far as build rates go.
Yeah, because it's one of those questions I've often asked myself. I came from the days where it was very low tech. The lasers we used were on or off. We didn't adjust spot size at all. It was just that was the spot size. I did my early research work on a 1 kilowatt CO2 laser that just happened to have a 1 millimeter spot size. And yes, we were doing lots of melting, but we had no idea what we were doing. But I hear about 2 kilowatts now in fiber lasers and think, well, what size can we get to that spot size? And will that really increase the productivity? And that's why I find the idea of the ring beam really, really quite exciting when you've got that much energy in quite a large spot size.
I think that's one of the big unanswered questions right now is people are going to be exploring with this 2 kilowatt ring mode is just how large of a melt pool can you drag around the around the powder bed and do it stably?
Yeah, keep it stable. Exactly. Without dragging in lots of contaminants and other things from that environment.
Yeah, I'm like I said, I'm excited to see what we learn and what we can gain from this, and I think we're just scratching the surface right now. So yeah.
And in fact, one of the other aspects I just remembered now about developing a system using this kind of technology is often people only think about the lasers and the materials interaction, and they don't think about the gas flow inside these.
Very critical.
Systems. And that has a big impact as well on the laser material interaction. If it's not optimal, then the smoke or the debris from the process will interfere with the beam. Is that something that you've had to study and take into consideration?
Yeah, of course. I mean, there's a lot of engineering that goes into optimizing the gas flow design and ensuring that it can keep up with this higher productivity and it can keep up with these higher laser powers.
And is it the same in both machines, the 3rd gen and
different platforms, different gas flow approach. So yeah, but a lot of effort's going into both of them. So
yeah, no, interesting.
Yeah.
Thank you.
Well, okay, let's thank our panelists one more time. Really appreciate you sharing your perspective. Yeah.
Thank you very much for having me, and thank you, Martin, for facilitating everything. Yeah. Thank you.
Thank you, Enlight.
Thank you.